Today we're happy to have Rohil telling us about quantitative elements. This is important.
All right, thank you. Yeah, it's been really nice to be back here. Thank you all for putting up with me. So, okay, so today is intended to be a bit of a technical talk, actually. I'm going to go in depth into one theorem from a recent preprint, which concerns dynamics of autonomous Hamiltonians in dimension 4. So this theorem is on this almost existence phenomenon. So the almost existence phenomenon for periodic orbits was discovered by Hofer and Zehnder the paper was published in 1987. And the theorem is the following. So let me fix some smooth and proper function H on the standard symplectic vector space. Then for almost every regular value S, the level set H inverse of S, which is smooth manifold of dimension 2n minus 1, contains a closed orbit of the Hamiltonian vector field X, which I'll denote throughout this talk by X sub H. Okay, and yeah, this is a very exciting discovery for a few reasons, actually. I mean, first of all, it's extremely general. It holds for essentially any Hamiltonian, which is maybe different from other results in the literature, which require often some kind of convexity assumption or, some various other assumptions on the Hamiltonian. And the other, maybe the other interesting part of the result is that it has, I believe their original proof was a variational proof using the action functional, but it was very quickly found to have connections to other parts of symplectic geometry. So just to summarize, so it was very quickly found to have connections to the theory of symplectic capacities. In just to say a word about this, I think, maybe this was restricted to the convex case, but it was found to be the levels that had orbits were found to be points of differentiability for the Hofer-Zehnder capacity. And there's also a relationship with Gromov-Witten theory and pseudo-homomorphic curves. And just to write some names down, it's actually very hard to write names down here because many people have made many interesting contributions to the almost existence theorem from the perspective of symplectic capacities. It would probably take me a couple more boards. In particular, this viewpoint has allowed extending this result to a lot of other ambient symplectic manifolds. And so Gromov-Witten theory, the story is a little shorter, so I can tell it in a little more detail. So in 1992, Hofer and Viterbo came up with a very nice argument involving next stretching homomorphic spheres to give another proof of this almost existence result. And then this was adapted in, I think, around pretty shortly afterwards by Liu and Tian.
When we did this, Gromov-Witten actually didn't exist.
Right, yeah. So this is maybe a bit anachronistic. That's a very good point. Yeah. I was going to say Liu and Tian actually, combined the Hofer-Viterbo result with the full formalism of Gromov-Witten theory. And then most relevantly for what I'm going to tell you about today, Fish and Hofer came up with another Gromov-Witten style proof of the almost existence theorem. This is a more, I guess, SFT-like approach in modern language. Yeah, so I'll just underline this. The Hofer, Viterbo, and Leotan approaches used some kind of Hamiltonian perturbations of the holomorphic curve equation. In particular, it's when you use higher genus holomorphic curves, it gets extremely cumbersome. So I've always found the Leotan work hard to understand, and I view the Fish-Hofer approach as I view this as an advantage of the Fish-Hofer approach. It's a little easier to work with higher genus curves from the point of view of SFT. Okay, so that's that. So the focus of my talk today is going to be on quantitative results. So let me just summarize what I know about quantitative results. So here by quantitative results, I mean almost existence of greater than one orbit. Okay, so yeah, so there's a lot of quantitative results, but they require some various restrictions on the Hamiltonian or on the level set. So for example, there's a lot of great results now for contact type Hamiltonians. There's another collection of results for level sets near extrema of H. So these are commonly known as, I guess, Weinstein-Moser theorems. Because the first instances of these kinds of results were proved by Weinstein and Moser, I think also in the 80s. And then there's also some.
It was 70s, I think.
Oh,
Moser
okay.
was 77.
Ah, I see.
And so Weinstein was shot a little bit before, maybe 76 or something.
Oh, okay. Yeah, my apologies. Yeah, I got the decade wrong there.
Yeah, it's pretty close.
Yeah. And then the last place where there's been a lot of progress is for I guess a specific type of Hamiltonian, the kinetic Hamiltonian on a magnetic cotangent bundle. So magnetic geodesic flows. I think there are very strong almost existence results for magnetic cotangent bundles of surfaces. I think Abbandondolo, Mazzucchelli, Maccarini, and Patternine proved below the Meunier critical value on any exact magnetic surface, you have almost existence of infinitely many orbits using variational methods. Yeah, again, if I'm not mentioning your name here, you should please tell me, and I will write it down. There's been a lot of great contributions to these kinds of problems.
Big remarks is Moser paper, I think if I'm not mistaken, is the one where he basically writes that flow theory can't exist.
Oh, really? That's fascinating.
Yeah, well, of course, he didn't know Floor, but he wrote that basically for technical reasons, one cannot expect this kind of, that there's a global theory for this kind of variational problems.
I see. Gotcha. Okay. All right, so now I will state a theorem. So now I'm going to restrict the dimension and look at a smooth and proper Hamiltonian on R4. Then for almost every regular value S, the level set H inverse of S contains at least two closed orbits. Okay, so at least in dimension 4, we're able to improve on the Hofer Zehnder result from 1 to 2. And there's a couple of things I like about this theorem personally. I like that it works for basically any proper Hamiltonian without imposing various restrictions. And the other thing that I like about this theorem is that in some sense it is sharp. In the sense that I can't rewrite this theorem with a 3 or a 4 or some higher number in place of it because there's an extremal example. So let's consider the Hamiltonian, which takes on R4, which takes x1, x2, x3, x4 to x1 squared plus x2 squared over a plus x3 squared plus x4 squared over b. And let's notice that if a over b is not rational, then each level set contains two closed orbits. Okay. So there's examples and even convex examples where every single regular level set contains exactly two closed orbits. In this case, these level sets are, I guess, the boundaries of irrational ellipsoids.
My question, when you say for almost every regular value, do you mean it's a dense set or it's like a bare category or? Like
I mean,
Measure theory.
I mean full measure, yeah.
Full measure.
Yeah, so yeah, almost every in the sense of measure theory. Yeah, that's a great question, thanks. Does anybody else have any questions about the statements or the examples? Okay. All right, and yeah, so I just wanted, before getting into, so I wanted to get into the proof pretty quickly, but before getting into it, I wanted to make maybe one more remark. Do that all the way over here. Yeah, so one remark that I wanted to make is, first of all, that this theorem was inspired by some results for contact type hypersurfaces in R4. So HWZ in 2003 and Christopher Gardner, Hutchings in 2016. They showed well, in kind of increasing generality, they showed any contact type level set in R4 has at least two closed orbits. Yeah, so yeah, so it can so this result could also be viewed as some kind of generalization of this to the non-contact type case. Okay. And there was maybe one more thing I wanted to say.
So that I'm sure that also works for C2H, yeah, is that true? If H has C2. What do you
That's,
know,
yeah,
C2
that's
plus
a good,
alpha?
that's a good question. Yeah, see, I think it should work for C2 plus alpha.
Yeah.
I think.
Yeah, so our stuff definitely works for that. And then there's this counterexample, C2 plus alpha Hamiltonian without periodic orbits. So you can also have in the family no solutions.
So that counterexample is stable, like you can find a
No,
family
so,
or.
no, then you just have one which doesn't have, and most have two at least.
Sure.
Oh.
See. Right.
So here you have two or infinitely many, and then others you have 2, 0, or infinitely. So,
Right. Yeah, the two are, I think me and Dan are thinking about the two are infinitely many in this setting, but we don't have anything to say about it right now.
yeah, so I could imagine when it should be possible to define ECH capacities, use ECH
Yeah.
capacities, and then generically deform the H so that the derivatives of these things are different.
Yeah, this was related to another general remark that I wanted to make. One really amazing thing in this setting is the connection to symplectic capacities that really stimulated a lot of progress The proof I'm going to show you does not use any symplectic capacities. And it's also a little complicated for my taste. I think it would be great to, you know, recast the proof in some kind of a capacity framework. I think that would be very interesting for future progress, maybe for extending these kinds of results to other symplectic manifolds.
Yeah, so maybe the result should be 0, 2, or infinitely.
Right.
Oh, gee.
That'd be.
So, I mean, almost everywhere, but you have to start in the neighborhood of presumably something which needs sort of that the capacities nearby, at least some of them have different derivatives.
Yeah, I guess, yeah, and since I mentioned other four manifolds, I guess I should mention one more thing, which is that, well, the proof does work for a couple of other four manifolds. So it also works for the cotangent bundle of S2 and the cotangent bundle of T2. I think you can probably do it for cotangent bundles of other surfaces, but other cotangent bundles have fairly different Gromov within invariants, so it's not entirely straightforward. Oh. Great. So where did there it is. All right, so let's get into the proof. So the proof is going to be some kind of elaborate contradiction argument. So first I'm going to make a couple of simplifications, and then I'll give our contradiction assumption. So just as a simplification, we're going to compactify R4. So we're going to compactify to think of H as a function on CP2. And we're also just going to localize to some small set of regular values and show that the set of hypersurfaces that have two orbits has full measure in that small set. So I'm going to assume that, you know, -1,1 lies inside the regular values of H. I'm going to define this notation. I'm going to define Y to be equal to the 0 level of H. And so by this assumption, all of the level sets in -1,1 are naturally diffeomorphic to Y. Okay, all right, so now my contradiction assumption is the following. So for almost every S in -1,1, H inverse of S contains a single orbit. Or sorry, not for almost every, for a positive measure. S in -1,1, yeah, we have only one orbit, which I will denote as gamma sub S. Of course, you could assume, of course, the correct assumption is that they have less than or equal to one orbit, but you could just appeal to the Hofer Zehnder theorem to know that for almost every S you have to have at least one orbit. So we might as well use it. Okay. All right. So the proof is going to involve techniques that are in some sense pretty old. You know, we're going to use holomorphic curves and neck stretching. So first I'll tell you there's some, you know, twists in both of these directions, both in the holomorphic curves that we use and in the neck stretching. First, I'm going to tell you about the type of neck stretching we do. All right, so this is a procedure called adiabatic neck stretching, which was defined by Fish and Hofer in their paper on the almost existence theorem. So first, what I'm going to do first is I'm going to define a symplectic four manifold W sub K by deleting this pile of energy surfaces. So, and then gluing in a neck, which is k times its length. So I'm deleting -1 cross y and gluing in minus k cross y. So how you should visualize it is I have this manifold W sub k with a really long neck. So let's put this as minus k, let's put this as k. And we're we're stretching along all the so you should think of it as we're stretching along all the hypersurfaces in this family at once. So if I look at a slice in this neck here, say KS, then you should think of this as corresponding to the level set at H inverse of S. Okay. And then on each manifold W sub k, we're going to fix some SFT-like almost complex structure J sub k on W sub k. I'm kind of hiding a lot here. You have to be fairly careful with how you do this, especially because you're not in the contact type setting. But by SFT-like, all I mean is that on the neck, the J sub k has some essentially standard form. So in particular, the ds direction will be mapped by J sub k to the Hamiltonian vector field, or some positive multiple of the Hamiltonian vector field along H inverse of S. So that's what I mean by SFT-like. If I can clarify further, if anybody would like.
It's like a constant multiple of the Hamiltonian, or like could vary.
It's like a positive function which you can make as close to 1 as you would like. Okay. So I've kind of told you about the neck stretching. Let me tell you about the holomorphic curves that we used. So we're going to appeal to a theorem which, well, I learned it from Tobbs. So we're going to fix any integer d greater than or equal to 1. We're going to fix any tame j. And we're going to fix some finite subset at S inside CP2, where the size of S is equal to d squared. Okay. So then I claim that there's a closed holomorphic curve satisfying the following properties. So there exists a closed J holomorphic curve, which I'll call U, CP2, satisfying a few properties. So first of all, U is going to pass through all these points that we selected. So S lies inside the image of U. 2, this will not be so relevant for our purposes, but I'll write it down anyways. The genus of the domain C is approximately d squared. And then the last point, which is going to be very relevant for our purposes, is that the symplectic area of this curve, so the integral of the pullback of the symplectic form, is approximately d up to some constant factor. Okay. So yeah, so we're going to have to work very hard actually to get our second orbit. We're going to need basically all of these moduli spaces of curves to produce this second orbit. Okay. All right. So now I'm going to consider my. So now I've defined the sequence of stretching almost complex structures, and I have these moduli spaces of curves for any d. So for any j sub k, I'm going to pick a sequence of degree d curves where d goes off to infinity, and I'm going to choose them pretty carefully. So here's what I'm going to do. So I'm going to choose, so I'm going to fix any d greater than equal to 1, and k greater than equal to 1. And I'm going to choose a set SD comma k as follows. So it's going to be a sequence of pairs S sub I, P sub I. This is just meant to indicate that all of these are going to lie in the neck. And what we want is that S sub I is in minus k comma k, and P sub I is some point in Y that does not lie inside the orbit corresponding to S sub I. Okay, so we're going to, or I guess I should clarify. So where H inverse S of I contains one orbit. So we're going to choose all our point constraints in these bad levels where we have exactly one orbit, and we're going to choose the points so that they don't lie on that orbit. And yeah, and eventually, and so eventually we're going to try and get some kind of contradiction. We're going to try and find some closed orbit through P sub I, and then by construction, it should never have been there.
Minus sign there, okay.
Sorry?
So k to the negative 1? I was like,
Yeah, we're dividing S sub I by K.
oh, yeah, well,
Oh, actually, you're right, I'm missing a
so
K
maybe-
here.
yeah, then I don't have to do
Yes.
so much mathematics.
Yeah.
Yeah.
Yeah, the K is just normalizing backwards. Yeah, so then I'll use Taubes' theorem with S d comma K, which I'll think of as a subset of the stretched manifold W sub K. And then we get holomorphic curves U d sub K.
So the SIs are just arbitrary d-square points.
Yeah, they're a collection of d squared points, but we're choosing them so that their corresponding level set is one of these bad level sets that contains exactly one orbit. Yeah, so they're not entirely arbitrary, but yeah, there's a lot of freedom in your choice. Yeah. Okay, so in the next 10 minutes, I'm going to introduce some fairly technical, I guess, notation or objects related to this. The point of this, so let me tell you what I'm going to do before I do it. So if you're in the contact type case and you have some sequence of curves U sub K, where K denotes a sequence of neck stretching almost complex structures, it's a pretty natural idea at this point to apply, say, the SFT compactness theorem and look at what dynamical information you can recover from the limit. We're going to do something similar here, except you don't have an SFT compactness theorem because we're outside the contact type case. Your curves can behave very wildly. But we're going to define some kind of analog of the SFT compactness theorem. And I mean, so copyright is still pending, but I'm going to call this thing the adiabatic limit set. Okay, so I'm going to define one of these for any d, so I'll denote it by x sub d. And it's a collection of pairs. So it's a collection of pairs which I'll write as S and C. And here C is a closed subset of -1, cross Y. And S is just some kind of height parameter. So this is just a number in -1. Okay, and how do I decide membership inside this adiabatic limit set? Is this too far to the right for anybody?
It's okay.
Okay. Well, I'm going to say that SC lies inside this adiabatic limit set if and only if there exists a sequence with the right as S sub k such that the following holds. So first, we want, after normalization by k, so k inverse S sub k, we want it to converge to S. And then second is, if we take our curves, if we take the images of our curves u, d, k, and we intersect it with S sub k minus 1, S sub k plus 1 cross y, we want this to converge to, C. I should just add in parentheses here after passing to a subsequence. This is just for technical reasons. And I'm putting a lot of weight on what I mean by converge. I'm sure somebody's going to complain about it right now, so I'm going to preempt that. So what do I mean by converge? So these are closed subsets of this non-compact manifold, Sk minus 1, Sk plus 1. When I say converge, what I mean is, first you translate these sets down by this parameter S sub k. So you get closed subsets of minus 1, 1 cross y. And then all I mean by convergence is convergence in the Hausdorff topology on the space of closed subsets. So extremely weak, not very analytical. So that's what I mean by convergence. Just something extremely weak. All right. Any further complaints? Okay. All right. So we're going to try and examine. So the idea is that under this contradiction assumption that we have this positive measure family with only one orbit, it's going to put some very extreme restrictions on the structure of this adiabatic limit set for large D. And that's ultimately what'll give us our contradiction. But before we get into that, I'm just going to tell you some properties of the adiabatic limit set that hold without, making these contradiction assumptions. And a lot of this is due to this Fish and Hofer paper. So to discuss this, I'm going to introduce some more terminology. So I'm going to introduce what I call blow-up sets. Okay, so there's two blow-up sets for every D. One of them I'm going to call the omega blow-up set. So this is B omega D. So this is a set of all S which have some sequence K inverse S sub K converging to S, and also have that the symplectic area of the level sets and also have that, there's some accumulation of the symplectic area of the corresponding level sets. So the way I'm going to write this is that if you take the limit as k goes to infinity of the integral of u dk inverse sk minus 1 sk plus 1 cross y of u dk star omega, and then I want this to be greater than 0.
Sorry, I come back to the complaining one.
Oh yeah, no, all complaints are welcome.
No, listen. So SK is between minus K and K, if I could.
Yes.
What does it mean K plus 1? Because you want to be in WK, which is exactly where you'd have minus KK.
Okay, maybe, I think in the paper, I probably just write, you take S sub K between K minus one and minus
Okay.
K plus one.
Okay.
Yeah, so you can, I mean, it's kind of the lazy way out, which I try to take when I
Basically,
can.
It's kind of you read
Just like
center and
strip
you
around
strip,
this.
yeah.
Yeah, I should add that the paper is much harder to read than my chalkboards precisely because of issues like these.
If you want to have that paper refereed in a lifetime, maybe you should work on
I'm not very optimistic.
it. Given the general trends in refereeing,
Yeah,
you have to take the referees by the.
yeah. Yeah, we're being recorded, so I won't say anything else, but I actually looked at my paper again while preparing for this talk and I had some, suggestions for my past self. Right, so blow up sets. So there's the omega blow up set. This tracks the levels on which you could accumulate some symplectic area as K goes to infinity. And then there's another blow up set called the area blow up set. Which I think I will skip the definition of. But it's kind of similar. It's the set of all S for which you have some sequence that where the area of the slices goes off to infinity. Okay. And I mean, the main thing I want to say is that having omega blow up and having area blow up is bad. It means you have lost control of your curves in that level. But I'm going to phrase this in a more positive way. There's a kind of general proposition which says that not having area blow up or omega blow up is good. And you can recover some dynamical information. So proposition. All right, so part A is what if you consider some S which is not in the omega blow up set, then this implies that for all SC in our stretched limit set, we have C is equal to something dynamic. So it's equal to -1,1 cross lambda, where lambda inside H inverse of S is XH invariant. Okay, I guess, yeah, so when we don't have omega blow up, we can actually recover some invariant subset. This could be a very complicated invariant subset. I've said nothing about it. In particular, it could even be the entire energy level. So there's really nothing ruling that out that I know of. However, there's part B. This is basically due to Fish and Hofer. If S is not in the omega blow up set and it's not in the area blow up set, so you have control of both your symplectic area and your, I guess, metric area, then what this tells you is there exists, you can recover something. So there exists some SC in S of D where C is equal to -1,1 cross a union of closed orbits. Right. Yeah, so if you have no omega blow up and you have no area blow up, you actually can recover periodic orbits. Okay.
So I'm sorry, what do you mean by area blow?
Yeah, I'm being a little bit imprecise just because, but I can be more precise. Let me write down a definition. Okay, so it's a similar thing. There's some.
So omega was a symplectic form. Omega,
Omega is
the symplectic form.
it's the ambient symplectic form on CP2, which becomes more, so which you can transport to these double stretch manifolds by natural diffeomorphism, but it does become more and more degenerate as you stretch the neck. So you shouldn't think of it as an area form because it's extremely degenerate. It's some.
And you have a two form on the energy surface, on the energy levels. That is what is concerned with the second. So you just look at the transfer, it's a projected area on omega. So that might go to infinity.
Yeah, so the area blowup is something similar. So yeah, with the J sub, with the almost complex structures J, you can define some kind of natural Riemannian metric on the neck. And so that's, I'll be, when I talk about area, I mean area with respect to that Riemannian metric. So this is the set of all S, which have again some, which have again some sequence K inverse S sub K going to S with but we're with the following property. We want that the lim sup or the lim inf again, as K goes to infinity, of the area of if you'll forgive me, I'm going to just write the S sub K slices to cut down on notation a bit. And we want this lim inf to be less than infinity. So there's some subsequence of slices where the area is controlled. Yeah, so I mean,
So the blow up would be if it's infinity.
yes,
And then if both are finite, then that is what you just discussed.
Yeah. Yeah, I guess maybe one very minor point is that if there's no omega blowup and no area blowup, we just recover one element of the limit set, which is a periodic orbit. If we wanted all of them to be periodic orbits, then we would have to change this lim inf to a lim sup or something like that. And we would have to change which have some sequence to all sequences like this satisfy that, and that is generally too strong to expect.
Sorry, the blow up means it's equal to infinity or less than?
Blow up is plus infinity.
Sorry. Yeah.
I think it combines the fact that you.
Yeah.
It's looked at finite.
Yeah. Thank you for catching that. Yeah. All right. Okay. So all right, so I've told you that when you don't have blow up, you can recover some dynamics. So you would like to know how big these blow up sets are. And and essentially how Fish and Hofer's proof of the almost existence of one orbit follows from this result, these combining this proposition with this one. So they show that the omega blow up set and the area blow up set have measure 0. So in particular, for almost every S, you don't have omega or area blow up, and then you get a periodic orbit on that level. Okay. All right. So that's everything that holds unconditionally. And now to get this second orbit, we're going to impose this contradiction assumption that we have some positive measure family with exactly one orbit. And we're going to see that this contradiction assumption puts much more extreme restrictions on the area and omega blowup sets than you might expect. All right, so as a preliminary step, let me do the following. So I'm going to write B0 to be equal to the kind of bad set. So this set of S in minus 1, 1, such that H inverse of S has one orbit. Which, just as a reminder, we're writing as gamma sub S. Okay, and so, and by our contradiction assumption is that B0 has positive measure. All right, so we want to simplify this a bit, or trim down this set a bit to one with slightly better properties. So I'm going to claim that there exists some compact positive measure set B inside B0 such that the following two properties are satisfied. So A is the function, so you can consider the following function. You can take a function on B0. You can take S to the minimal period of gamma sub S. Okay? And we're going to trim down the set so that this minimal period function is continuous and bounded. Okay? And then similarly, there's a
So this we can achieve by taking arbitrarily small epsilon measure set away.
Yeah, this is a consequence of Lucent's theorem.
Yeah, it's I remember I studied this as an undergraduate.
Oh. Yeah, when I was writing the paper, this kind of thing is a very embarrassing mistake to make. So I did a lot of reading to make sure I did not mess it up. But yeah, the second property that I want is that there's kind of you can also consider the symplectic action of these orbits, and you want this to be continuous as well. So I can consider the function S goes to the integral gamma sub S of nu, where d nu is equal to the restriction of omega to R4. And I want this to be continuous, bounded, and also positive.
So the maps will have to be measurable to begin with.
Yes, so you can show that this set is measurable. And then you can show that this function is lower semi-continuous, because if I have a sequence of S sub k converging to S, where the minimal period is bounded, then the corresponding orbits will converge to a cover of the gamma sub S in the limit, so that could have lower minimal period. And then lower semi-continuous functions are thankfully measurable.
Okay, I see you have it all covered.
Yeah, I was very worried about this part. So yeah, so I think the most suspicious assertion that I'm making is actually that this symplectic action is positive. There's no real reason you would expect this outside the contact type case to begin with, unless your orbit bounds a symplectic disk. But in this case, by this Fish-Hofer approach, all these orbits gamma sub S are coming from holomorphic curves. In particular, they'll bound a holomorphic curve they'll bound some piece of holomorphic curve in the in the compact part of the hypersurface. So you get the positivity from Stokes' theorem. Okay. All right. So with this in mind, now I'm going to state two key lemmas about the blowup sets and say a little bit about their proof at the same time. All right. So lemma 1. So maybe I'll be very precise in what I say. So I'll write B star to be equal to the Lebesgue density 1 points. In B. Then my claim is that if I take the arts of the omega blow-up set that lie inside B star, then this is bound, then it's actually finite. It's bounded by some D independent constant times D. So this is a very strong restriction because all we knew about the omega blow-up set before is that it has measure 0. In particular, it could be infinite. I think you can do a little better than what I wrote there. You can show the omega blow-up set is countably infinite. But here we get a very explicit bound, at least on the part inside the bad set. Okay, and the proof is some kind, and the proof, I can basically give a picture. So the point is that if you're in the omega blow-up set, so if you accumulate some symplectic area, then the amount you can accumulate is actually quantized. Because so let's look at some S in the omega blow-up set. Then we can choose two nearby levels, S plus and S minus, where the holomorphic curve looks like, you know, some multiple of gamma S plus and some multiple of gamma S minus. Okay, gamma S, by our kind of continuity assumption, gamma S plus and gamma S minus have very close symplectic action. It's you know, they're very close to a single number. So, but these multiplicities M plus and M minus are integers. Okay, so either they're the same integer, in which case you can show that the omega energy is very small and it doesn't accumulate, or they're different integers. So by assumption, we can actually show, by assumption of blow up, we can actually show that M plus is at least one larger than M minus. And so that gives some kind of.
What do you mean by this? So the intersection, what do you measure of this? The lemma, you write ED intersected with this.
Yeah, with the space of.
The number, what is it? Is it the state? What is it? What do you measure? No, in the second line.
Sorry, the number of points.
Okay, no.
Yeah.
Yeah, that's makes sense.
So the rough idea is that there's if the symplectic area blows up, it has to blow up by some non-trivial amount, some h bar, but our total omega energy or symplectic area of the entire curve is on the order of d. So there can only be on the order of d places where you have omega blow up. Okay, so that's key lemma 1. Now, lemma 2 addresses the question of area blow-up. Because we want to produce closed orbits, but we can't do that if we have area blow-up. Okay, so the claim here is actually that if I take the points of area blow-up intersected with B star, then they're actually inside the omega. So roughly speaking, the way I state this is that area blow-up actually implies omega blow-up. And the rationale is the following. So let's suppose that we have a point S, which has area blow-up, but has no omega blow-up. Then, by this structural proposition A here, my limit set at height S has some invariant subset C, which is not a periodic orbit. On the other hand, my holomorphic curve on nearby levels produces periodic orbits with bounded multiplicity. in particular, taking limits of those approaching S actually shows that you have some copy of gamma sub S in your limit set. And then it's not super clear from the definition, but from the definition of the limit set. But after passing to a suitable subsequence, you can assume that the limit set at height S is connected. So what this tells you is that I actually have some family of invariant sets interpolating between my periodic orbit and of which has finite period and this invariant set of infinite period. But so in particular, this connectedness argument would tell me that maybe I have some periodic orbit gamma whose period is an irrational multiple of the period of gamma sub S. And that's a contradiction by our assumptions. So in the end, we get that by this kind of connectedness argument, we get that there had to have been some omega blowup in the first place. Okay. How do people feel about that argument?
What assumption we started with? Like, what assumption?
So I assume that there's this positive measure family V0 with one orbit, and then I made all these simplifications. So I trimmed it down to something where the minimal period of gamma sub S is continuous and the symplectic action is continuous.
Okay.
And then I also even looked at the Lebesgue density 1 points, which roughly mean that the point of doing this is to show that you have lots of nearby levels with exactly one orbit. Okay. All right, so we are almost, with combining these two lemmas, we can finally get the contradiction that we want. Okay, and all right, so I'll give the proof of theorem, assuming lemmas. Okay. So by the lemmas, the size of the blowup of these two blowup sets, at least when you intersected with D star, is bounded above by D. Okay? And so in particular, if we take D much bigger than 1, then we have one of our D squared constraints, S sub I, P sub I, as S sub I not lying in the union. So what this tells us by part B and the fact that the holomorphic curves always pass through this point P sub I is that we get a period, is that there exists a closed orbit through P sub I. And that is a contradiction because we specifically chose P sub I to not have a closed orbit through it. And just to conclude, I should say something about the order of operations. So the logical order of this proof is a little complicated. In particular, I did write some things in the wrong order. So in particular, I chose my point constraints and then I defined this trimmed down set B star. So that's actually not allowed. But this is actually easy to reverse. I mean, nothing about this definition of the set depends on holomorphic curves. So if I was presenting the proof in the correct logical order, which I did not for expositional purposes, I would have defined this trimmed down set first and then chosen my point constraints to be inside this ultimately trimmed down set B star. All right, so that's just the last comment that I wanted to make about that. Okay, well, yeah, thank you all for listening.
Question? So the only thing you need for dimension 4 is the Taub's theorem, or
Yes, yeah.
can you say what the property you needed again, like the d square?
Yeah, unfortunately that disappeared, which
Um,
it would have been helpful for the proof, but so you need, so I'll write this a little informally. So through any d squared points, there exists a closed curve with symplectic area bounded above by d. And that's basically all I used. You can actually, you can say some more about the curve. For example, you can specify the arithmetic genus of the domain. But we don't end up actually needing that here.
But if you go to higher dimensions, then there should be also some existence results, but the numbers are not that great.
The numbers don't work out as well. Right, so for this, what's special about 4 dimensions here is that you can get the symplectic area to asymptotically be less than the number of point constraints. But for example, for CPN, I think if you look at the Gromov-Witten theory there, then usually the number of point constraints will grow linearly with the symplectic area, I believe. So, I mean, you could still.
Yeah, because of that, 1 minus g times 2n, that is bad. So in principle, one would just need a device of producing holomorphic curves in your strip, sufficiently many. Is that correct? It's sort of.
Yeah. So I think, so Dan pointed out to me that this argument probably works in, say, 4-dimensional symplectizations. Because you can.
But I'm interested in higher dimensions.
Yeah. Higher dimensions is. So under interest.
Yeah, so the nice thing of dimension 4 is that you can get holomorphic curves from closed cases, which is easier to handle, because you don't even know if you can't do that, and you have to come up with boundary conditions or all kinds of things to produce them. There's no machinery yet. But I would think this kind of results should also be true in higher dimensions. It's just that we haven't developed the right machinery.
Yeah, I'm quite optimistic about it, but there are some clear problems.
Of course.
Yeah.
Like red with the freaking holomorphic curves.
The higher dimension, the expected bound is not 2, it's like n.
Yeah, I would be happy with 2, but but that's a very good comment. I mean, probably if you can get 2, you have a good chance of getting n. Or just to repeat for the audience, maybe the correct conjecture is for Hamiltonians on R2n for higher n. You want almost every hypersurface has at least n closed orbits.
And then, so the classical work in the 60s, they studied, for example, autonomous Hamiltonian systems and genericity results for them. And you have the cylinders of periodic orbit going through them. Then you have period bifurcations, and then they do the same stuff again. So what we're describing here is part of that picture, yeah? So if I look at this generic things and make a sort of a stretching construction, to look at it, then we're looking at certain parts of that picture. So what they describe are really Hamiltonian systems on symplectic manifolds. They didn't know contact type that was important and so on. And they just show generically we have there's a lot of literature.
Yeah, what you're describing should live inside this adiabatic limit set. You should be seeing these families.
When it's like a family, so you can have things which on an energy surface do this and the period blows up. And others have bifurcations and so on. But of course, the period only blows up at very few places because with respect to measure. And what you in some sense do is you look at a certain part of this. but there has to be a bigger picture. Maybe one should
Yeah.
study this, because they are not only the periodic orbits, they are the closed subsets and so on. So maybe it would be sort of an interesting project to look at this generic situation, what they describe, and then just focus in on all kinds of things.
Yeah. I think as I mentioned earlier in the talk, the proof is a little too ad hoc for my taste. I think I think putting it in some kind of more general framework would be very, very interesting.
Also, maybe I missed completely the point, but kind of tops us up in 4 dimensions. If you want to push it in higher dimension, the thing you use is basically that you can find on each set basically a point which is not in your orbit. I mean, that's much stronger. You say for any point because you pick it randomly, but can't you think about, I don't know, picking points on level set in a very strong configuration, because you have a high dimensions, you have a lot of freedom, and say maybe, I don't know, they are on some algebraic curves or related something like this, which do not intersect orbit, and then maybe you have more control on the holomorphic curve.
I think I got lost in what you were saying. So
I'm saying the PIs that you take on each level, which I think of it as h minus 1 of SI. I think, if I understood correctly, basically the only constraint you need is PI is not on the orbit, the single orbit gamma of SI.
yeah, but remember, we're making this contradiction assumption at the very start. So ultimately, we're not showing that you can. I mean, so I guess what you're getting at is in the contact case, there's this result by Christopher Gardner and Mazzucchelli, which says that if the contact action spectrum is rank 1, then you're actually Zoll. You can produce periodic orbits through anywhere. Because this argument is so non-constructive, I can't recover anything like that.
No, it was that was not what I had in
Oh,
mind.
okay.
I thought during the high, I was trying to mimic your argument and say somehow the only point where it screws up in high dimension, if I get it, is to prove there is a closed curve with symplectic area less than the number of points.
Yeah.
And I was kind of saying, during high dimension, so you redo the argument, you have your h minus 1 of SI, assume you have one orbit in each of those, and then you say, okay, now my contradiction is because there is a holomorphic curve going through each of my PI. But if I understood correctly, but maybe that was hidden, you kind of choose your PI randomly outside of the orbit. And that's a.
I thought they had to line this best set. It's not super random, right?
I mean,
Yeah, there's an order of operations. I mean, you have to choose the point constraints first, and then the blow-up sets are determined after that. So
yeah, I was just trying to say, could you imagine choosing your point? I mean, maybe it's completely crap what I'm saying, but can you imagine choosing your point in a much, I want to say, constructive or clever way on each level, such that if you look a step back, all the points are, I don't know, related by some algebraic curve or something, and then suddenly you have a control on the holomorphic curve, which is there because you've chosen points very carefully and not just somewhere. That was my.
Okay.
Like not trying to generalize terms, but just trying to.
Thank you for explaining. Yeah, I see. Yeah.
I mean,
I think I need some additional processing time, but it sounds interesting.
So, can you maybe explain where the argument fails if you look at like points that don't lie on 2 orbits?
But yeah, I guess it has to fail, certainly.
Yeah.
But let me think. I think it's not that there's any issue with choosing the point constraints. I think these key lemmas might fail.
What's the question again?
If you take the same construction, but consider the bad level sets, the one that have exactly 2 orbits. and then try to prove that there are more than two.
Let's see. Yeah, I think probably. Oh, yes, the lemma one on this bound on the omega blow up set will fail. That, I can explain a little more, but that's the one that will fail if you assume there are two orbits instead of one.
Maybe we thank Rohil first and then